Award of a number of prestigious journals. He has won loads of prizes, chairs the IHL's Fluid Mechanics Committee, and if you want to read all his achievements, his biography is in the programme.
Thank you, Sarah. Good morning, everyone. Thank you all for being here. Specifically, much thanks to Aras for this invitation. And I think we all forgotten to also thank him for the nice place and the great organization. So, don't take that from my time, please. All right, let me see. I need to get this going. Okay, let's start with a video and see how you like this. First, it's going. It's coming from the dead, coming back. Now, let me guess what you feel like. You feel thirsty, looking forward to tonight's dinner. Most of you. But all of you, I'm betting you say, that's not going to happen. That will not happen. Well, as we will discuss a bit later, actually physics say it can happen. The laws of physics do not prevent that. And that was the great debate, Boltzmann's time, in fact, where this was why are the basic laws of physics reversible, but nature doesn't seem to be. Boltzmann finally, after 20 years of work, he came to the answer. He says it can happen, but the probability is very small. Okay, so the probability is much higher that it will not. So that means if you wait a million, maybe 10 million years, that might happen. And maybe that's why we don't live that long, because otherwise we'll see crazy things happening. Now, it so happens that actually waves, on the other hand, waves are robust to time reversal. You do reverse waves. And I got this quote actually from the book that I'm sure all of us got into this field because they read it by Wiley. And it's a very interesting read. It says the Warhammer equations are remarkably robust in calculating backwards on time. That is, a residual transient can be utilized as the initial condition, and you're solving back in time. So he's saying, yes, it is time reversible. But of course he adds and says, the idea though of calculating backwards on time defies logic, since it cannot be done physically, because of damping. So it can be done on the computer, but supposedly it cannot be done. What I will show you is already some examples that, yes, damping is there, but actually the waves are nearly reversible. And you will see these in some videos that we started. And that very realization actually became a huge technology in ocean engineering, ocean acoustics, ocean imaging, medical imaging. I'll show you quite a few of these examples. It's all based on these ideas of time reversal. We in Transient, I think, used it indirectly for valve stroking. Liggett's method of adjoint operator is somewhat based on that. There is a lot of things that we use, but we are not actually, perhaps, we did not think too much and exploit some of the ramification or some of the, basically the consequences of this reversibility. So what is the basic idea? The basic idea is this: with waves, if you have a source, we know the waves will spread, and you could have a non-uniform media, and you measure the pressure at a couple of locations. What you do, you take this signal and reverse it in time. What does it mean, reverse it? Last in, first out. Okay, what you receive last, you send back first. And if they are reversible, you should see that the waves actually collapse back to the source. They go back to their origin source. Now here is a video showing this, that it can happen actually in gravity waves. So what you will see now is they're going to generate, so that's the source. Okay? So the waves are emanating radially. And what they are doing here is they're going to measure the pressure at about 3 locations here. Not everywhere. And then they're going to take that signal and reverse it back. And quite interestingly, now I'm going to be stuck here. Freddy, if you don't mind, can you move it? Because otherwise we'll wait for a long time. To about 45 seconds. So in about 45 seconds, about 35, actually what they did is they recorded that signal and they send it back. They send it from 3 points, and let's see what happens. Does it actually go back and reverse to the source? This paper, when it came out, actually received a lot of attention in the media and stuff, because it was not expected. So you see, nothing seemed to be interesting happening. Now remember, they are sending the waves back from these ends. Okay, so the waves are reversed and sent back to the medium. So nothing interesting yet happening. Okay, in fact, it looks may not lead to anything, but that's the nature of these type of problems. So I don't know if I guess I hope I'm not blocking anybody. Okay, I know it takes a bit of time. Sorry, bear with me, but it's the end product is worth it. Okay, so it doesn't really look like going anywhere. Well, now I hope you start to see something interesting is happening. Something interesting, and there you go. Okay. Now, what you basically see, though, is that you see still a lot of the waves in the background, but the main one actually came back. So why are there this what we call later side lobes? You see, these side lobes are there simply because when you measure 3 points, you did not capture all the energy. Some of the energy you're not actually sending back, so you did not capture all of them, but you're still getting the essence because it's closed cavity, and some of it is due to noise. So you will see with this time reversal there is always some waves. You did not capture all the waves to cancel each other out. So now let me move down to, let's see, where's the next one? Now the next one is, well, how about electromagnetic waves? Are they reversible? So what this video will show you is what these people do is they send a source from here, they measure these 4 points, and after they do that, they reverse it, and you should see the same thing happening. So it's fun, eh? Lots of videos, nothing to worry about. I have actually no objective except showing you a few videos. Okay, so that's the forward. I don't think there is anything in there that would be surprising to this group. So let's now go to about 35 where they reverse it, 35 seconds. Now you. Okay. Sorry, you'll have to then bear with me here. Okay, now they go to the reversal stage, so that's the points. And again, these waves are doing what waves like to do, bounce from boundaries, trapping all the energy, and just keep your eye on here, because we want the energy to focus back on the source. Sure enough, but again, you get the side lobes. Okay, happening on all of these. Now, acoustics. This was done again by a French group. By the way, the French are actually leading in this field. And what they do is this in the room where again they generated the source here and they measured at all these locations. So I'll skip the forward problem. We are all familiar with the forward problem. Here's the inverse problem or the time reversal problem. So now after they measured the pressure in a room, they send back these pressures, and again, keep your eye on what things will eventually happen there at the source. So it seems all of these waves are always coming back to rediscover their origin. Okay, they are going home. A bit of structure, and there it goes, and physics work. Okay, now this idea actually, the first test that was done in the ocean was about in the 90s. It was in the Mediterranean Ocean. It was both the French group and an American group that did these tests. And what they did is they send these waves and they measured it about 30 kilometers away. Okay, acoustic waves. And then they, not large amplitude at all, and then they send these waves back, and sure enough, they focus on the source, 30 kilometers away. Okay, and now that's a big technology in terms of ocean imaging now and communication in ocean. Because when you get data inside in the middle of the water, how do you communicate? Wireless is not a good option. High frequency, it dissipates in water. So acoustics is the best way. Fish know that. Right? Another technology that actually emerged out of this is for kidney stone. Because what they do is they send a test wave. That test wave then reflects off the stone. Once the doctor gets that reflection, they now time reverse it and send a large amplitude. Then the wave focuses on the stone and destroys it, and does not destroy anything else. So you get this time reverser to guide the wave to where it wants to go. Now, how about for us? What can we do with this water hammer? We did this in the field. We have a 3-fire hydrant where we will send a burst light here, and we measure at these 2 fire hydrants and see again if we can time reverse this. And you will see some faces you recognize here, okay, in this conference, helping out. And this one you might recognize, many of you, Duncan McInnes, who is sending the source for us. So now this is what we measure. So we send a burst, we measure these 2 pressures passing by. So what we do next is time reverse this. So okay, we time reverse the signal and then send it back. And when we send it back, you should see this wave now starting to feel it, start to be felt here, and then you'll see your drop. You rediscover your drop that you send at the right time. So it does refocus back. So we can do this in pipeline. By the way, this is an interesting one. This is in Hong Kong about 2 years ago. They decided to test real-time measurements. They were sampling at about 300 hertz, and they were doing it real time. They're catching all the data in their mobiles, watching their pipeline. And by the way, yesterday we discussed the data mining. So just data alone was actually interesting for the engineers. You didn't have to mine it because they did not know that their system was that dynamic. Suddenly they actually see that the system is lively. It's changing all the time. Because most, I think, undergraduate students, they think steady hydraulic gray line. They realize that that's actually far from reality. But anyway, one of the interesting things is every day, and this is Hong Kong, we are punctual. Almost at 4 o'clock, they see if a drop of a pressure of about 15 meters, for a few seconds it goes up. What's going on? Is somebody stealing water? What is going on? Why are we? And that was regular every day. And this became, it was actually a dead end, and they were measuring at these 2 locations. So it was a nice testing ground for us. So what we did, we mimicked that pressure at this source and that source, the same pipeline, and we reversed the signal to just see what actually happened, to see if it tell us where the source is. Okay, so we took essentially more or less what they kind of observed, we put them here, and they are time reversed them and hoped for the best is what will this give you. And let's observe. Okay. And now we see this is where, that's the source of the signal. Where the signal organizes, where the source. And that happened to be, in fact it turned out to be, that's where there is a fire hydrant. And what was happening every day at 4 o'clock? There is this tank here that comes every day at 4 o'clock, which the water supplies department didn't know about it. And it opened the fire hydrant, they fill the tanker, and they take it for street sweeping. And that was regular every day at 4 o'clock. Okay, so it told them that there is somebody else taking their water. Now, we wanted to see in pipelines what happened if we send very high frequency waves. So we sent a wave at 7 kilohertz. And the reason 7 kilohertz is now you don't just have the water hammer wave, the plane wave, you actually have radial waves. So here we excited the water hammer mode, the first mode, and the second. The first mode, the water hammer mode, travels along the pipe. The first mode goes in a zigzag motion. It bounces up and down. So it actually lags behind. It will slow down. So you see the water hammer beating them. That's the fastest. Right? And the second mode actually zigzags even more. So it will be the third. So we send them, of course, when you send the signal, you're going to send them together, but you will see them sorting themselves out. Okay, so that's the forward. Let's run the forward. There you go. You see Usain Bolt is the water hammer wave. It's beating all of them. Right, and the first mode and then the second mode, and we are measuring here. We're measuring at that location. Okay? So what we do is we're going to measure at this location and now reverse that signal. I do time reversal and see what we get with it. Okay, now it repeats itself. So this is what we measured essentially. The versus time, the water hammer wave, the first mode and the second mode. Now we're going to take this, reverse it, flip it back in time, and send it as a source and see what we get from it. All right, let's see. Going, yes, it's going. So now you see the third, it's reverse, so the third mode first, then water hammer wave is already catching up with them, they both catch up with one another, and right at the source, they both recombine and give you what we send out. Okay, so it is. Now, what does the physics say about this? The physics, in fact, says the Newton laws are blind to time. You change t to minus t, nothing changes. The energy equation is blind to time reversals. The energy equation stays the same. Your wave equation stays the same. Let me see. Well, of course, Maxwell's equations stay the same. That's why they were reversible, one of the examples. Quantum physics is time reversible. That's the Schrödinger equation. The Navier-Stokes equations are time reversible, in this end, are time reversal. So nonlinearity does not break down time symmetry. You got minus v, minus v. So there is nothing wrong with, so nonlinear waves are also reversible. Here, the Navier-Stokes equation, I denoted that with minus. It seems there is a problem with reversibility of viscosity. But this is where, remember, physics is reversible at the particle level. When we are modeling Navier-Stokes, we're looking at the continuum level. And in a continuum, this is not basic physics. That term did not come from basic physics. That comes from our experiments. It's our output of viscosity. So we are building in already the irreversibility that we expect into the equation. So essentially, this is what's called Lock-Schmidt paradox. Lock-Schmidt was a colleague of Boltzmann, and the two of them basically fought like there is no tomorrow. And Lock-Schmidt said this. He said, according to the laws of physics, if I measure that glass of wine, if I measure at a point in time, I measure all the molecules, their speeds, then reverse that back in time, I would get back the glass. Because the Newton laws are reversible, the energy is reversible, they don't tell me anything else. I don't care, because molecules don't see viscosity, right? Molecules just bump to one another. Okay, so, but still that's somewhat, so what is the current understanding? Here is a nice experiment that was done in Paris, actually, not my experiments, this is by Matthias Fink. He put 2,000 steel bars randomly, and then send a wave from here, and measure the wave at this end. So these waves will ricochet, of course, and bang all around. He measures them, and that's what you see there. Then now he time reverses them experimentally and sends back, and you do get back your signal. So although they go through this myriad of bouncing, they actually already discover it. Now then, this guy Schneider in the US did these experiments where he sent no particles. He wanted to see what happens with particles. So let's send particles, and he put scatters in the middle, and he observed here their speeds, and what he did, then he took that speed and he reversed the speed and the direction, and see what happens. Well, what happens, a couple of them do go back to the source, but many of them are all over the place. And then it hit him. He says, what's going on? It's chaos, nonlinear dynamics. Nonlinear dynamics means particles are sensitive to small errors in initial conditions. So Lock-Schmidt, essentially, even if you measure the particle, as long as you make any small error, the errors will grow exponentially, and you cannot reverse things back in time. What they proved now is that for waves, those perturbations grow as a square root of t. So they are quite robust. You only lose it after a long, long time. But for a short time, they are quite reversible. So what does it mean to us? Mathematically, it means if your head at xt and q at xt is a solution, this is also a solution, right, of the equation. And Fedi will be talking tomorrow. Actually, there is a a mathematical tool that was actually created in the 70s in acoustics based on precisely this. Because we know if there are two solutions, then any linear combination is a solution. And mathematicians have a field day with that. They have lots of fun making up all kind of intricate ways of using that. I think Professor Wiley in his book says that essentially if you measure at a certain time, you can work backwards. Well, in fact, if you can measure at any curve, that's not a characteristic. You can reconstruct the history and predict the future. So that measurement, and we saw experimentally that the energy refocuses back at the source. So what does the math actually say about this? Simple math. So let's say you have a source, you send the source into your pipeline, that's a delta function, and then you measure the response. We call it a response, mathematicians call it G, Green's function. So what you're going to do now is time reverse it. Send it into your pipeline and measure the response. So what is your response? Is your reverse signal convolved with your response function? That's what the response function is. If you write that integral, you get, this is what the convolution integral is. I hope you can notice that this term here becomes maximum at t equal to 0. T equal to 0 is where you send your source. And that's why these waves always focus back at time equal to 0. So how does it work out for us? So for example, take the case of a leak, one leak, and then you have a reservoir, you get reflection from the leak, you get reflection from the reservoir. So now imagine your time reversing it, and then what are you going to see? You're going to see those waves going back, they go back. Here they both join one another. The reflection from the leak and from the reservoir, and they're going to go in tandem together to time equal to 0, and they refocus at time equal to 0. All right, so that's essentially the idea for it. Let me skip this. So how do we do this in the math? Essentially, this is the change in head due to the presence of the leak. It's scattering from a leak. This is the size of the leak, and it's a function of its location. Now, time reversal in the frequency domain becomes complex conjugation. So we just take, instead of time reversing it, you just take the conjugate in a complex space. And since we measure over many frequencies, and then we have a vector of these measurements, then you take the transpose. So this H here is the conjugate transpose. But what you do is you multiply both sides, essentially you convolve, because convolution in the frequency domain is a product. So you multiply by both sides, and then you solve for SL. Solve for SL, put it back, and you end up with an equation that only depends on the leak location. Okay, so you are trying to find where that leak is that will give you the wave to focus back at time 0. Essentially, where is that target? So when you plot it, essentially will be, and this is an explicit function, right? There is no guessing here, there is no optimization, because this is a one-dimensional, and this is a hyperbolic function, so sine of XL, cosine of XL, so we can plot it. So we plot and just look graphically even where the peak is. And where the peak is, it's telling us where our reflector should be. Okay, that's essentially how. Now, the width here, interestingly, this width here, if there is no noise, but of course there is noise, as Jim says, the width here is lambda over 2, the wavelength over 2. Wavelength over 2 is what's referred to as the diffraction limit in quantum physics, or the Enquist theorem. So there is a limit. Essentially, when the wave is converging back, it does not reach a point. It starts to reflect. Okay, causality, and then it keeps going. If we play those videos, you see the wave starts to go outward again. When there is noise, which we do, what happens with noise is this becomes broader. Okay, so that means you're losing localization. Okay? So, and this becomes flatter, so it's not peaked at one point. So you're starting to say, well, my leak is here, but there is an error associated with that. And we'll see what are the ways of dealing with it. How can we make this sharp, essentially thin, and how can we make it sharp, right? What are the ways, the technical ways to deal with it? So, in reality, as Jim made a good point earlier, there is noise. So what happens to this methodology when there is noise? Well, in fact, in a recent paper, we proved that it's still, the search is still optimum. It's optimum in the sense that how it works, it maximizes signal to noise ratio. Okay? That's what this time reversal will do. Always maximize your SNR. So here is some data from Italy where we applied it, and you see you get the peak at the right place, and you get the side lobes. Remember I told you the side lobes? Those are coming from the fact that you did not measure all of the energy and send it back, and some of it is from noise. And we will see what are the ways to also deal with that. So now how does actually, just think of what's happening, how does it actually work? So let's say you guess a leak, this is a true leak, and you are guessing where the leak here is. Of course, when you send your wave, because you guessed your leak here, so the first, you're going to get a reflection from the reservoir, and you're going to get the reflection from the leak. But the reflection from the leak, because you guessed it at the wrong place, is not going to converge, it's not going to focus at 0, it's going to focus at an earlier time. But I'm interested in what focus. The theorem says look at time 0. So what I report here, that's the only energy I'm getting at time 0. So I plot that, that's my B. Okay? Then I move my location, and then when I put it in the right place, then I say, all right, well, when the leak is in the right place, the runabout is in the right place, there they go, they meet, and I get the two of them to add up. The reflection from the leak, the reflection from the reservoir adding up, and my B increases. That B function, I'm looking for where this peak is. Now we also used our lab in Hong Kong, and our lab, the nice thing turned out is that it has a lot of noise, because then it stretches these methods quite a bit. We get clean data from Italy, we get a very crazy data here, but it's actually telling us that the system is quite robust. So here, interestingly though, on the right-hand side, we did not account for viscoelasticity. And look at what happens. It kind of found where the leak is. The red bar is where the real leak is, and this is what we are finding when we are plotting that peak. So we do find a peak near it, but it's shifted because our wave speed is wrong. We did not account for viscoelasticity, but we get many leaks. So what's the model trying to do? The model is trying to create fictitious leaks that will compensate for the losses. It's fine, it's finding lots of losses, and it thinks that there's a leak. So it says here there is a leak, here there is a leak, and when I make up all of those leaks, they seem to give you enough damping equivalent to your viscoelasticity. So we go and we add back the viscoelasticity, and things become much better. Then the right place, and you get the real peak at the right location. So of course, right physics is very important. Then we tested this with three leak sizes, and we did the comparison with a variety of techniques, ITA, the wavelet, and by far, this time reversal is the most robust. So 96% of the times, Schuren conducted 150 tests, 96 are within 1 meter. You localize the leak within 1 meter, and about more than 100% is within, I'm told that I'm running out of time. So now how do we deal with these side lobes? What you deal with side lobes is how do you make them thinner, and how do you suppress them? Do multiple measurements. The more you repeat the transient. If you can repeat the transient, it sharpens your localization, and it kills all the side lobes. Now, how much time do I have?
Approximately 0.
Okay.
2 minutes or 0.
All right. So here's for when we have multiple leaks. We can actually search for multiple leaks using one leak. And how does it work? Essentially, so this is what you know, of course. If you measure the reflections. So now, what we do is we say we don't know how many leaks actually, so you guess one leak. You send back, and let's see what happens. Because you guessed it in the wrong place. So again, you get to the reflection for reservoir, but all the other ones are off. So then you plot your B. Whatever you're getting, you plot this guy, and you plot what your B is. Then you move it to the right place, and suddenly you're gonna get, now the reflection from the reservoir and the leak are actually coming back together, and you will see a peak. And then when this moves again to the next one, you get another peak, so you get a double peak, and you say, okay, well, I think I have 2 leaks in this system. So how good does it work? Let me skip through this. We tried this, and it works really well until you get to about 0.5 of whatever your probe and wavelength. Once you are within less than that, your localization cannot separate the two. It sees that there is a problem, but it cannot separate them into individual leaks. Let's do this. And let's see with data. So with this data, we have 2 leaks. So with 2 leaks, you see what has happened. This is when we model with only 1. We search with only 1. Here when we search with 2. Here when we have a model searching with 3. It seems they all agree, but what do you do in this case? You want something to tell you. Well, what tells you is actually this likelihood function. When you plot the likelihood, it says beyond 2, you're gaining very little. So there is this AIC, which is archaic information. When we plot it, it's minimum at 2. It's telling me that in fact there is 2 leaks in this, in what you're doing. That was done with 3 leaks. I'll just scan through this. This one, if you give me 1 minute, because it's not our work. It's actually very interesting work. Done by this lady, Alexandra Tolstoy. She has, in my mind, the best introductory book in the area. Alexandra is actually an ocean acoustician. She did all her work, but after retirement, I guess she found this problem to be interesting. And in her paper, she's thinking of blockages in sewers. So what she did is did this experimentally. She's I think a physicist with no hydraulic training. So she wanted to localize blockages with no model. Okay? So what she did is she did a concrete pipe, a PVC pipe, and she measured, of course, before the blockage. She sent a signal, measured what comes back, and then she put the blockage. And her blockage was actually just throw some stones in there, right? Or some sandbags, irregular, and she measures the signal. So now what she does is uses exactly time reversal. But now, remember, what I've been showing you, we're looking for the time where you get the energy to focus. Now she's saying, because I have the measurement with no blockage, the measurement with, I'm going to look for the time at which we lose coherency. Where I lose coherency, that tells her the time where a problem occurs. Then she uses the wave speed to tell her where the problem is. And that's what this basis is. So you see it's almost 1, 1, 1 normalized, and then you got to lose here. So things drop, and it's at this location where the problem is, and that's how she localized, both in PVC. And so this is the methodology where there is no model, it's just data. Okay? I will skip this. Fedi will show you how you apply this to blockages. And then I don't even need to read this. I'll leave it for you to read, and thank you very much. A nice book. It's a nice book.
Once again, I thought it was better to let our keynote speakers speak for an extra time rather than ask questions. So again, if you have any questions for Professor Ghidaoui, please can you discuss them during the breaks. And can we once again thank all of our speakers. And I hope Ali will tell you what time we need to come back up.